Thank you, Dawn. Thank you, everyone. Good morning, everyone. My name's Nick Metherall. I'm currently completing my PhD through a joint program between the University of the South Pacific in Fiji and the Australian National University. And today I'm going to share a presentation about digital Earth Pacific and cloud-native approaches to detect mineral extraction activities in Fiji. And I'd just like to acknowledge our collaborators here, Alex Leith, Kishan Kumar and Sachindra Singh. So I'm going to cover these areas in this presentation, just the background, some of the key objectives of what we were trying to do, the different indices we trialed, where we've learned from and the different approaches, a logistic regression approach as well as a multi-class random forest approach to classify mineral extraction. I'll then speak a bit about how we've used change detection and some of the wider applications for digital Earth Pacific and our next steps. But before I do so, Dawn's correct, I didn't submit a bio, so I'll just talk briefly a bit about my background and how that kind of has supported me in this work. So in the past, I've worked with the Department of Environment in Canberra and the Northern Territory, and have done some research. This was kind of a literature review that pulled together collated information about the legacy mining in Australia. So legacy mines are defined as abandoned, orphaned and derelict mines, and Unger et al. Estimate that there's more than 52,000 of these in Australia. And this is probably an underestimate because there's a lot of missing data and lack of reporting. And so I've done a bit of research on that at a large scale, but I've also worked with the supervising scientist branch in the Northern Territory monitoring the impacts of the Ranger uranium mine and we did this report on the impacts of magnesium sulfate flows into the groundwater, the surface water, and the impacts on fish migrations. And this work wouldn't have been possible without our teams and people we've learned from, including the park staff, Indigenous rangers, and the supervising scientist branch. So I was thinking about doing my PhD up in the Northern Territory, but I ended up, I was kind of worried mainly because of the crocodiles. So I ended up putting out a few grants. I did a lot of work with Water Watch and I put out a few grant proposals and I ended up getting one. And it was actually to go over to Fiji. And so my PhD looks at the spatial prioritization of waterways and riparian ecosystem services in the Bar River catchment in Fiji. And this is composed of three components: riparian corridor monitoring, waterways, that's my hydrology background, as well as some of the impacts of tropical cyclones. One offshoot of this has been the environmental impacts of mining activities, and this has been really well summarized in this report from the UNDP, which basically summarized that about 34% of communities surveyed found that there were some impacts on their coastal fisheries and their village-managed fisheries from river mining. And so the government in Fiji is seeking to phase out in-river mining, but there are challenges for them because they can't always get out to these really remote areas and monitor every single river because of the spatial and temporal constraints on the work that they're doing. So Earth observation is a potential additional line of evidence that can support this work and maybe help them to prioritize where they should survey and where they should monitor. So there's really a few components to this. This is an example where you'd have a stone crushing plant with impacts on the downstream water quality. You also have the impacts of building these access roads into rivers and the clearing of riparian vegetation. I'm going to draw on this case study, but what we've tried to do is to really scale this across all of Fiji with the potential applications to scale more widely. And so this case study is called the Dawa Samu catchment, which is in the northeast of the main island of Viti. And it's the largest stone crushing plant in Fiji. So there's this, as I mentioned, the stone crushing, but also these access roads where the trucks come in and extract. And this has been covered in the media because there are cases where the government will put out stop orders to stop the companies from mining, but they might continue to mine at night or they might continue to mine even when there is a stop order. And so how can we monitor this? And I think that this is where Earth observation has a lot of strength to be able to monitor the symptoms of mining. And so when I say symptoms of mining, I'm really talking about, these are some examples for before and after. For the site, you have clearing of riparian vegetation, completely distorting the geomorphology of the river. You have much greater levels of turbidity and sediment transport down the streams. We've done studies where we've actually taken water samples throughout the whole day and measured and done gravimetric analysis in labs to measure that sediment impact on the downstream fisheries and other ecosystems. And this kind of just shows those peaks in turbidity throughout the day. So, in this context, our objectives were to create another tool to provide an additional line of evidence to monitor in-river gravel extraction using Earth observation. And this could be used for compliance, enforcement, and to deter the violating of mining licenses and going outside of the mining areas or mining when you're not supposed to mine and things like that. Originally, we were focused just on rivers, but the scope later expanded to also cover land-based quarries. So, in terms of remote sensing, we started off with just looking at a range of different indices and different approaches. We used a bit of Earth Engine, but we also then for scaling and for reproducibility, we worked with Digital Earth Pacific, which was a Jupyter environment. So, we had a lot of data on water quality for turbidity, as mentioned. So we started off looking at turbidity. There were some limitations because of the sizes of the rivers and the spectral resolution, the resolution of the satellite imagery for Sentinel. And another challenge we had was it's hard to disaggregate the impacts of mining from other impacts of, say, a tropical cyclone that might clear a lot of forest and increase runoff. So these were our challenges. We ran a lot of analysis all over Fiji on different rivers and did show there were some statistically significant relationships between the establishment of mining sites and increased turbidity, or NDTI. However, again, it's hard to say whether it was just because of the mining or also because of a tropical cyclone that cleared a lot of forest. And that was the same issue we had with vegetation indices as well. Looking at the impacts of clearing from mining, it's hard to disaggregate from this loss you can see here from a tropical cyclone. So that was another challenge for us. We're also really interested in looking more into temporal segmentation, which can help us to detect points in time where the change is occurring, and this can shed light on more stories at a much more micro level. So the establishment of the stone crushing plant, for example, here, where there's degradation and then some form of remediation or reforestation. And we can use this on various micro sites, the pit level of the mining, or other sites, but it becomes harder when you're trying to look at it across a wider scale. So for a wider scale, we looked at classifiers. And so a lot of this work, we've worked with my colleague Kishan, who's here with us today. And he did a lot of great work on using logistic regression, or max-ent, to try to have a kind of a binary class, yes, no, is there mining, is there not mining? And this involved a lot of exclusion of masks and different layers. And Kishan developed a GUI in Earth Engine, which was really useful. And so we wanted to build on this to kind of help us to better discriminate between, or disaggregate between, naturally occurring gravel bars and extracted stockpiles. And so that was one of our main challenges. So we tried a multi-class classifier in random forest, learning from examples like some of the work from Digital Earth Australia. We also looked at Digital Earth Africa. However, these are large continental scales, very different contexts to some of the rivers in Fiji. So we had to kind of adopt more tailored approaches. Again, some of the key points where you have different symptoms of mining. You have the access roads and the clearing of riparian forest. You also have these large stockpiles. And so what we tried to do was to develop two separate classes for these. A class for bare lands, shown here in brown, and a class for stockpiles, shown here in red. And through this approach, we were able to help reduce that noise and that confusion and better isolate where you might have stockpiles and where you might have access roads or naturally occurring sediment or bare soils. So we had one version which is just a regular land cover model that shows all these different classes, and another version which just isolates the brown bare lands, red stockpiles, and the blue water, which is often used as in mining processes. And this helped us. This is the Sambeto River. Using this process, we can start to see the red isolate these areas where there are stockpiles, and also try to isolate these areas where there could be those access roads where the extraction is actually taking place. This is another example of a Lion 1 gold mine close to Nandi, and it shows the area of the expanding pit of mining. So with change detection, we can show this expansion. This base map is from the current year, but the expansion is shown here in orange. So you have orange, which is the expanding mining, yellow where there might be some rehabilitation or regrowth of vegetation, and this maroon dark red, which is the color where the quarry is consistent across both years. So you see going into 2022, 2023, you see the established mine and the further expanding areas. And this can also be used for the in-river gravel extraction. At this site, we see where the light brown is where there's an expanding mining area or the expanding bare lands. The green is where there's regeneration of vegetation, and the dark brown is where the mining has been established. So we see that in the early years, 2018, there's a lot more mining downstream, and then as we move forward, that expands, and then 2020, 2021 as well. But as we get into 2022, you can see that the mining has actually moved far upstream. And so this would be something that the Mineral Resources Department could then go and monitor if the company is moving outside of their license permit area. So that just gives an example of that. All of this was developed through a cyclical workflow that involves collecting training data. So a lot of the work was involving labeling data, annotating data, collecting data in the field with QField based on, or site observations, fitting that, cleaning that, and then fitting it to satellite imagery, GeoMads developed by Alex. So we had to make sure they aligned, and then using that to train the machine learning model. And we can use a range of different models using scikit-learn, and then running predictions and doing accuracy assessments. But a lot of the time really just went into that cyclical workflow and generating more and more improved models and more improved training data. So we did about 32 iterations and through the Python notebook environment. And what we found was that through the feature importance, that these were the main findings. We found that elevation, shortwave infrared, bare soil index, and shortwave infrared, the other one, were the most significant features. Again, this was all developed through Digital Earth Pacific. I think many of you have seen Sachin's presentation on Digital Earth Pacific, so I won't cover that again. And what we teach is, what we run through Argo workflows and the Kubernetes clusters is this simplified workflow of training the model, running the prediction for these various years, and then doing change detection for each of those years to help us to detect this mining. And this is enabled through the DEP computational capacity, through those Argo workflows. And these kinds of processes are what we will use what DEP will use to meet a range of different needs cases, not just mining, but these are the needs based on what the countries have requested through a needs assessment process. And so the applications from this mining, we hope will be useful for a range of this change detection approach. Some examples here. I mean, this example is really just land cover and mining, but similar workflows can be applied to other sectors, such as, you're detecting some of the environmental degradation here in small areas, but then you have, this is a bauxite mine here, you have this coastal development here detected, as well as, again, even timber plantations, so monitoring deforestation and monitoring commercial timber. So these are some examples of other applications of the work that we're doing. In terms of next steps, we want to continue to improve upon this. We want to really deepen our understanding of how we might use more temporal segmentation, continue to learn from our colleagues at Digital Earth Australia, Digital Earth Africa, and maybe even Digital Earth Antarctica we have here today, and also to look at a range of other models and other approaches, clay and other ML models. So, with that, I just wanted to say thank you very much.
Thanks, Luke. So we have plenty of time or lunch. So just bear that in mind. Does anybody have a question? Yay, thank you. It always helps to have somebody start them.
Okay. I read an article a while back about illegal sand mining, and I can see that this is probably related to, has anybody actually tried this out, or can you see the application there?
Thank you. Great question. That is an issue as well for many of the contexts we're working in, sand mining. I think that, again, we would have some of the challenges disaggregating between naturally occurring sand and sand banks and things like that, and then the sand mining areas. But I think that maybe some of the access roads that might go out to these could be detected. Perhaps if there was maybe a stockpile class that we were able to detect some difference in maybe texture, depending on the size of the sand stockpile. We could try that out, but it is something that probably will be a request in the future. I know that that's an issue for many of the countries we work in, including Tonga and Fiji, but and I'm sure it's an issue more widely here as well. But yeah, I think that it would be quite a similar approach, but there would be those challenges that we talked about with disaggregating. Thank you.
More? Yes?
Thanks, that was really interesting. My question is about resolution. What's the scale of the resolution that you're working with? And particularly, I was looking at your image of looking at change along the riparian areas back along the river. Like how finely resolved and how accurate does that get?
Definitely. So yeah, I should have mentioned, but we are mainly working with Sentinel-1, Sentinel-2, so it's just 10 by 10 meters. So of course that is tricky when you're working right up in the upper tributaries or like the smaller gullies where you might have issues with detecting those changes. But usually if there are access roads, you should be able to detect some change, but 10 by 10. And stockpiles can or may not be that size, but you should detect some change there.
If we have pause now, I am sure Nicholas would be very happy to talk through any questions that anybody has on the Geoscience Australia web stand? Or is it all Digital Earth?
Digital Earth Pacific.
Right. So that one over there. And you will have plenty of time to do that since you can now run away and lunch will be served at 12:15 and sessions start again at 1:15. So thank you very much for coming. Please join me in thanking Nicholas. Sorry.